So in this lecture, I want to review some results that we already proved in light of the previous theorem. So I will first recall the theorem, and then I'll go to the applications. So the theorem we proved concerns the following. We have an array x and j running from 1 to kn of, so this is an array of independent random variables, and I'm assuming that kn converge to plus infinity, and I'm assuming that these variables are uniformly negligible in the sense that if I take the probability that x and j it's larger than delta, I consider the maximum in j. Well, this quantity it's converging to 0 for all delta positive. And the question we addressed in these last lectures was to find conditions which ensure that the sequence of random variables, so the sum of x and j from 1 to kn, minus a sequence of real numbers an, converge in distribution to some random variable s. So we wanted conditions, sufficient conditions on these random variables to ensure that this quantity will converge in distribution. And what we have seen is that this happens if and only if the triple, which I will define in a second, m tilde n, 0 bn, converge to a triple m sigma square b. So I have to define what is m tilde and what is bn. So I'll first define a and j. So a and j is the integral of all x d mu and j for x less or equal than 1. So mu and j is the distribution probability measure associated to the random variable x and j. So nj is that. So now we define the random variable x tilde and j, which is x and j minus a and j. And we define mu tilde and j to be the probability distribution associated to the random variable x tilde and j. So this is m tilde and j, and mn tilde is the sum of these measures, these probability measures. So this is the measure m tilde, which is appearing here. It's a Levy measure, and here is its definition. Now I have to tell you what bn is. So what will happen here is that we will subtract a and j and add a and j, and therefore bn will be equal to an minus an. So an, let me define it here, is the sum of a and j. And bn, so it's an minus this an and plus the integral from minus, so the integral of theta x d mn tilde of x. And this is in R. And, well, theta x, remember, it's the function which looks like x for x between minus 1 and 1, and it's a continuous bounded function. So what we require is that theta x minus x, it's bounded by a constant x cubed for x bounded by 1. So bn is this quantity, and what we proved, and I will recall the proof in a second, that, well, this sequence converge in distribution to S if and only if this triple converge to that triple, so that there exists a Levy measure M. So what this statement is saying is that there exists a Levy measure M, a non-negative constant sigma square, and a real number B, such that this triple converge to that one. And by convergence, you remember we have three conditions. This means actually that three objects converge. And I will come back to this in 1 second. So this is the theorem. So I'll just remind you of a proof of this theorem, and then we will apply this theorem to Poisson convergence and Gaussian convergence to recall the Lindbergh condition. So let me remind you the proof of this result. So what we first do is that we replace x and j by x tilde. So for that, remember that x tilde is x and j minus a and j. So I can rewrite this expression as x and j tilde plus the sum of a and j minus a n. And this is what I represented by a n. So this expression converges in distribution to S if and only if this one converges in distribution to S. And then, well, what was the advantage of working with x tilde? Because for x tilde, if we defined a and tilde j in the same way as we defined a and j, which means that we take the integral for x less than 1 of x d mu tilde and j, now we have a very useful bound that a tilde and j, so that there exists a constant C0, a finite constant C0, such that for all j between 1 and kn and for all n, this quantity is bounded by this quantity. And this condition was used in the proof of the next step. So this is why we moved from x to x tilde, just because we have this inequality. Now, once we arrived at x tilde, we defined y tilde and j as the Poisson transformation of x tilde. So this is, well, I won't define precisely, but we introduced y tilde and j as the Poisson transformation of this random variable. And we proved, and this was an important, well, long demonstration, a long proof, that this expression converges to S if and only if the same one, but with y tilde instead of x tilde, converge in distribution to S. So that was an important step, and in this step we used this inequality. Now, once we arrived at this quantity, well, we can compute the characteristic function of this random variable. So if I represent by fn tilde of t the characteristic function of this expression, what we have, because y is the Poisson transformation of this random variable, we had this expression for this first piece. So we have here the sum j of the integral of exponential I tx minus 1 d mu tilde nj. So this corresponds to the characteristic function of this quantity, and then we have this constant, and this constant will provide a plus I t an minus an. And of course, now we can introduce the function theta. So remember, the sum of mu tilde nj is the measure mn tilde, and here I can introduce the function theta x, which looks like x close to the origin, so that here what I have, it's an expansion up to the second order. So this function close to the origin will behave as x squared. And this is important because mu n maybe doesn't integrate at x, but it integrates x squared. So here is mu n tilde. So mu n tilde, remember, it's the sum of the mu tilde and j. And since we introduced this expression, we have to take it back. So this is plus it and it theta x mu tilde n dx. So this is, we subtract it, now I'm adding, and we still have plus an minus an. So this is the characteristic function of this quantity. And now mind that this is exactly the characteristic function associated to the triple m tilde n 0 and bn, provided bn is this real number which appeared here. And then we proved that, well, this random variable converge to a distribution f if and only if the triple m tilde n 0 bn converge to a triple m sigma square b. So if and only if there exists a Levy measure m, a non-negative real number sigma square, and a real number b, such that this convergence happens, and in that case S will be the random variable associated to this triple. So we had in this proof two important steps. The first one is that this expression converge if and only if that one converge, and a second step is that a random variable whose characteristic function which is associated to a triple converge if and only if the triple converge. And so this is the theorem I wish to apply to two different contexts: the convergence of Poisson, the convergence to a Poisson distribution, and convergence to a Gaussian distribution. So you have to keep in mind this result during this talk, because I will be referring constantly to this result. So my first application will concern to Poisson convergence. And what we have here, it's an array x and j of independent random variables, kn it's converging to plus infinity, and the distribution of these random variables is as follows. Well, these variables take only the value 0 and 1. The probability that x and j is equal to 1, I'll represent that by p and j, and this is 1 minus the probability that this random variable takes the value 0. So these are the random variable. So my first claim is that the sequence is uniformly negligible if the maximum in J of P and J converge to 0. So let me prove that this condition holds if this maximum converges to 0. So uniformly negligible, remember, means that I want to estimate what is the probability that x and j it's larger than delta. And I want to show that the maximum in J of this quantity converges to 0. But in our case, since this random variable takes only the value 0 and 1, if delta is less or equal between 0 and 1, say, the probability that it's larger than delta means this is equivalent that the probability that x and j it's equal to 1. Well, of course, if delta is larger than 1, this probability is just 0. And this, by definition, it's P and j. So you see, if we want the maximum in j to converge, of these probabilities to converge to 0, we need that the maximum of p and j converge to 0. So I will assume that this condition holds, and it follows from this condition that this array of independent random variable is uniformly negligible. Now, I want to observe what I claim, my second claim, is that if that a and j, so that there exists a finite constant c0 such that a and j, it's bounded by c0 times the probability that x and j, it's larger than 1/2. Which means that we don't need to go from x to x tilde in order to guarantee that this condition holds, because it holds already for the random variables x and j. So let me prove that. Remember, a and j, by definition, is the integral for x less or equal than 1 of x d mu and j. Mu and j is the distribution measure of the random variable x and j. But since this random variable takes only the value 0 and 1, actually this integral is equal to the integral of x. I don't need to impose this condition that x is less or equal than 1, because un is 0 outside this interval. And well, this is the expectation of x and j, and the expectation of x and j, it's p and j. On the other hand, this probability, the probability that x and j is larger than 1/2, it's equal to the probability that it's equal to 1, and so this is p and j also. So this inequality holds with c0 equal to 1. So as I said, since this inequality holds for the sequence x and j, the array x and j, I don't need to go from x to x tilde, and I can apply the first theorem to say that, well, the sum of x and j minus an converge in distribution to some random variable s if and only if the sum of y and j minus an converge in distribution to this random variable, where y and j is the Poisson 1 transformation of the random variables x and j. So now let's write the characteristic function of this quantity. So we have seen, let me represent by fn, the characteristic function of this random variable, and we have seen that this characteristic function is the one which is associated to mn. Now I don't have the tilde, and 0 and bn, where bn, it's equal, since we didn't add an is 0, and so bn is just the integral of theta x mn dx minus an. And therefore, this sequence converge in distribution if and only if this triple converge. And now I'll make precise what I mean by this convergence. So if we want to investigate this convergence, what we need is to investigate this convergence. So for this convergence means that we have three conditions. The first one is that for all function f, which is continuous and bounded, and such that there exists a delta strictly positive, such that fx it's equal to 0 for x less or equal than delta, then the integral of f with respect to mn converge to f dm. So meaning that we have three conditions. So saying that this triple converges to another triple means that these three conditions are satisfied. This is the first condition. So we have to examine, take a function f satisfying these two conditions, and let's see if this sequence of integrals converge. And for that, I hope you remember the assumptions. Let me erase that so that we can compute this integral. So remember, Mn is the sum of the measures mu and j. So fix a function f satisfying those assumptions and consider the integral of f with respect to Mn. So this is the sum of g of f with respect to mu and j, and this is equal to the sum in j. This is the distribution measure associated with the random variable x and j, so this is the expectation of f, x, and j. And this expectation, it's equal, so x and j takes the value 0 and 1. Well, but f, it's equal to 0 at 0, and then takes also the value 1. So this is the sum in j of f1 times the probability that x and j is equal to 1, and this is p and j. So if we want this integral to converge, we need that the sum of p and j, which I'm calling Pn, converge. So if Pn doesn't converge, this integral will not converge, and if Pn converges, this integral converge, and it converges to the integral of f with respect to a measure, which is the measure concentrated, the Dirac measure concentrated on 1, multiplied by p, which is the limit. And of course, this limit, it's, well, since Pn it's non-negative, this limit it's a non-negative real number. So if we want this expression converge to this one, if and only if Pn converge to p. So I need to add this assumption in my set of assumptions. And now my claim is that if this, well, this condition is necessary and sufficient for the convergence to hold. So we have seen that it's necessary. Now let me show that it is sufficient. It's necessary because if it doesn't converge, this expression doesn't converge, and therefore it's not true that this triple converges to this triple. So now I'm including this assumption in my set. And what I proved is that this occurs where m is equal to p times delta 1. So now let's go to the second. Well, the second condition is that there exists a x0, which is a continuity point of m, as well as minus x0. So here I can take any number different from 1. So I need that there exists x0 such that the measure of minus x0, x0, it's equal to 0. So both are continuity points of m, and such that the integral from minus x0 to x0 of x squared dmn plus sigma n squared, but sigma n squared here it's 0, converge to the integral of x squared dm plus sigma squared. So this is the second condition when we mean that this triple converges to that triple. So in our case, well, let's take x0 equal to 1/2, and let's see, I'm taking 1/2, but I just want to take any number less than 1 so that the limit of the right-hand side will be 0. So let me take x0 equals, say, 1/2. But as I said, any real number between 0 and 1 would be fine. So x0 1/2, it's certainly a continuity point of m. Now we have to check that this limit converge. So minus x0 or minus 1/2 of x squared dmn. Let's compute this limit. Well, this is equal to, by definition of mn, this is a sum of the integral between minus 1/2 x squared d mu nj. But mu nj puts positive weight only to the points 1 and 0. 1, it's outside this interval, so there is no contribution. And at 0, x squared is 0. So this is identically equal to 0. And therefore, since this integral it's equal to 0, we have indeed that this expression is converging to that expression, provided I take sigma square equal to 0. So I have already obtained what m has to be in this limit. I now obtained what sigma square is in the limit. And let's go to the third condition. The third condition concerns Bn. So now the third condition is that Bn converge to B. And well, let's recall what Bn here. Theta, remember. So let me remember you that theta x, it's a continuous bounded function, which looks like x. So one possibility, one example was the function which is equal to x between minus 1 and 1, and is equal to 1, or the sign of x outside this interval. But what's important here is that theta, it's a continuous bounded function. And so we want Bn to converge, so we need to consider the integral of theta x mu n dx minus an. Mn, again, is the sum of theta x mu nj dx minus an. Now, mu n puts weight, only weight, positive weight at 0 and 1. Theta at 0, it's 0. At 1, it's theta 1 with weight p and j. So this is equal to p and j times theta 1 minus an. And therefore, this is Pn, so this is converging to P minus A, provided that An is converging to A. So we need An to converge because we already assumed that P and J is converging, the sum is converging to P. So if An converges to A, we have that the sequence Bn is converging to P minus A. So M, it's P delta 1, this is 0, and this is P minus A. So this sequence converge, which means that this sequence converge to S, which is the random variable associated to the triple P delta 1, 0, P minus A. If and only if Pn converge to P and An converge to A. So let's, so this is the result. We have that if Xn satisfies these assumptions, so P and J, the maximum of in J of P and J converge to 0, and the sum of P and J converge to P, we have then that this sequence is converging in distribution to this random variable. So let me just write what is the characteristic function which we obtained here. So the characteristic function associated to this triple, let me write it as phi of t. It's the exponential of the integral of exponential I t x minus 1 minus I t theta x dm, but dm it's p delta 1 dx minus sigma square t square divided by 2, but this is 0, and plus I t P minus A. P theta, I'm sorry, I'm missing here theta 1. So this is, I made a mistake. I forgot about theta 1. So let me add, so this is actually P theta 1 minus A. And here, this is P times theta 1 minus A. And so here it's theta 1 minus A. And, well, but since this measure it's equal to that, I can just rewrite this as the exponential. So it puts mass 1 at 1. So this is exponential IT minus 1 times P. Then I have here minus IT theta 1 P, and then plus IT P theta 1 minus A. So this expression will cancel with that, and I have here minus ITA. And so, well, this is the characteristic function of a Poisson random variable with parameter P, and this is the characteristic function of the constant A. So actually, this is converging to, if I represent by n a Poisson random variable with parameter P, this is converging to n minus A. So under the assumptions that the sum of P and J is converging to P, and that the maximum in J of P and J is converging to 0, we have proved that the sum of x and j minus an is converging to a Poisson random variable of parameter P minus A if an converge also to A. So these are necessary and sufficient conditions for this sequence to converge to a Poisson, to a random variable, and in that case, if it converges, this limit will be a Poisson minus a constant. So this is a first application of the theorem we proved in the past lectures. So in the second part of this lecture, I will discuss convergence to a Gaussian distribution. So remember, if X has a Gaussian distribution with mean mu and variance sigma square, then its characteristic function phi of t is given by the exponential of minus sigma square t squared divided by 2 plus I t mu. And this corresponds exactly to the characteristic function associated to the triple 0 sigma square mu. Therefore, if a random variable S, which has characteristic function associated to the triple m, let's call that maybe S square, and B is Gaussian, so if this is the characteristic function of a Gaussian random variable, well, by uniqueness, we know that this happens if and only if m is equal to 0. So a characteristic function associated to a triple m s square b, it's the characteristic function of a Gaussian random variable if and only if m is equal to 0, because we have seen that the characteristic function of a Gaussian is given by this expression, which can be represented in this way, and therefore, by uniqueness, if m does not charge 0, we know that these two characteristic functions are equal if and only if m is equal to 0, s squared is equal to sigma square, and b is equal to mu. So we have a very simple characterization of the characteristic functions of Gaussian random variables. And we will use this fact in order to investigate the convergence of random variables, or some of arrays to Gaussian distributions. So here is the first result which I want to prove. So assume that we have a family, an array of independent random variables. And here J runs from 1 up to Kn, which is converging to plus infinity. And we will assume that this sequence is uniformly negligible, which means that the maximum over J of the probability that x and J larger than delta, that this converges to 0 for all delta positive. Now let me denote it by Sn, the sum of these variables, x and j, and let's assume, so I'm assuming that this sequence converges in distribution to some random variable S. And my problem is to find sufficient conditions and necessary conditions which guarantee that the limit S has a Gaussian distribution. And the result is the following. So my claim is that S has a Gaussian distribution, so it's distributed according to a Gaussian random variable mu sigma square for some mu and sigma square, if and only if the sum from 1 to kn of the probability that x and j is larger or equal to delta, that this converges to 0 for all positive delta. So you see that we started from the assumption that the maximum of this probability is converging to 0. Now, what this result is saying is that, well, if the sum of these quantities vanish, then the limit has a Gaussian distribution. And this is also necessary. So if the limit has a Gaussian distribution, then this sum vanishes. So we have a very simple criteria to guarantee that the limit has a Gaussian random distribution. So this is what I will prove next. So I just rewrote the claim. We have an array of independent random variables. They are uniformly negligible, and I'm assuming that Sn is converging distribution to some random variable S. Then the claim is that S is Gaussian, so it has a Gaussian distribution, if and only if this sum converges to 0 for all positive delta. So let's prove this claim. Let's start, let's say, with this direction. So I'm assuming that this probability is converging to 0. Now, let's say Sn is an array, a sum of independent random variables which are uniformly negligible, and I know that Sn converges to S. Then from the theory we have seen, we know that this happens if and only if the triple mu n tilde 0 bn converge to a triple m sigma square, and let's call that mu. We have seen that these two statements are equivalent. So Sn converging distribution to a random variable S if and only if this sequence of triples converge to a triple, and in this case, the random variable S is the one whose characteristic function is associated to this triple. Now we know, so in order to prove that this random variable S is Gaussian, we have seen that we need to show that m is equal to 0. So that this random variable S is Gaussian if and only if m is equal to 0. Therefore, if we want to show that the limit is Gaussian, what we need to show is that m tilde n is converging to 0. Well, so what we need to show is that this integral, the integral of f d m n tilde, it's converging to 0 for all f which belong to the space C, B star R. And remember, we introduced this notation before. C, B star R, it's the space of continuous functions which are bounded and which vanish in the neighborhood of the origin. So this means that there exists an epsilon positive such that fx is equal to 0 if x is less or equal than epsilon. So these are the bounded continuous functions which satisfy this identity for some positive epsilon. So this is what we need to prove in order to show that m is equal to 0. Now, what I claim is that it's enough to prove that if I take that for all epsilon, the characteristic function of minus infinity minus epsilon union epsilon infinity d mn tilde converge to 0. If I can show that this sequence converges to 0, then I can prove that for any bounded function, I have this because, it's easy to bound f by a constant times the characteristic function of such a set if f belongs to this space. So if I can prove that this quantity converges to 0, I can conclude that these integrals converge to 0 for all such f. So this is what we need to prove. But in order to prove that, let's recall what m tilde n is. M tilde n, it's the sum. So this can be rewritten in terms of the random variable x tilde s and j as the sum from 1 to kn of the probability that x tilde n j is larger than epsilon. So what we need to show is that this sum converges to 0. Let's rewrite this sum in terms of x and j. So this is the sum over j of the probability that x and j minus a and j is larger or equal than epsilon. Now we know that the maximum of a and g converge to 0. Of actually the absolute value of a and g. So we can choose n0 sufficiently large such that this maximum is bounded by epsilon over 2. So let's restrict our attention to this n for which this maximum is bounded by epsilon over 2. In this case, this probability, it's if x and j minus a and j is larger than epsilon and the maximum of a and j is smaller than epsilon over 2, this means that x and j has to be larger than epsilon over 2. So this is so under this assumption, this probability is bounded by this one, and therefore this sum it's bounded by this one. Now we know that by assumption, we know that this quantity here is converging to 0 for all delta. So actually it's true for delta equal epsilon over 2. So we know that this quantity here is converging to 0, which means that this one is converging to 0, which is this one, and therefore we just proved that for all function f in CB star of R, we have that this sequence is converging to 0, which means that indeed m is equal to 0, and therefore that the random variable S has a Gaussian distribution, and therefore we proved the first piece of this claim, which tells that if this sum is converging to 0, then the limit here has to have a Gaussian distribution. Now let's prove the other direction. So we assume that S has a Gaussian distribution, and we want to show that this sum converges to 0 for all delta. The proof is very similar and relies on this fact. So since we know that S has a Gaussian distribution, we know that M is equal to 0, which means that the characteristic function of S is associated to the triple 0 sigma square mu. Now, since Sn is converging in distribution to S, we know that this sequence of triples is converging to that triple. Therefore, M tilde n is converging to 0, and this means that for all functions f in Cb star of R, we have that the integral of f dm n tilde is converging to 0. So now we go, essentially we will repeat the same argument as before, inverting the order, so going backward in the argument. So now we know that this happens for all functions f, and what I claim is that, well, since the limiting is 0, all points are continuity points, and therefore, for all epsilon positive, we can also conclude that the characteristic function of the interval minus infinity minus epsilon union epsilon plus infinity d mn tilde, that this is also converging to 0. Right, because since minus epsilon are continuity points of the limit, we can approximate these functions by continuous functions. We have seen that before, so it follows from this assertion that the assertion can be extended to this type of indicator functions. And, well, if now we recall the definition of M tilde n as we did before, what we know from this is that the sum of the probability that x, so let me write x and j immediately instead of x and tilde, that x and j minus a and j is larger than epsilon, that this converges to 0. Now, again, let's assume we know that the maximum is converging to 0 as n tends to infinity. So let's assume that a and j is bounded by epsilon. And let's consider the probability that x and j is larger or equal than 2 epsilon. And what I claim is that if x and j is larger than 2 epsilon and a and j is smaller than epsilon, then x and j minus a and j has to be larger than epsilon. So that this probability is less or equal than this one. So let me repeat. If you know that x and j is larger than 2 epsilon, and you know that a and j is bounded by epsilon, then the difference between x and j has to be, in absolute value, larger than epsilon. So this probability, this set is contained in this one for n larger than n0, and therefore that probability is bounded by this one, which means that this sum is less or equal than that sum, but since this sum converges to 0, then we get that this sum converges to 0, and this is exactly what we wanted to prove. So by using this theorem, which was presenting necessary and sufficient condition for the sequence Sn to converge in distribution, we proved the claim that the limit is Gaussian if and only if the sum of these probability converge to 0. So you see that we have a very simple characterization of the fact that the limit is Gaussian, and an interesting one, because we started from uniformly negligible random variables, meaning that the maximum of these probability converge to 0, and with the stronger, much stronger assumption that not only the max, but the sum of this probability tends to 0, we get that the limit is Gaussian. And this condition is not only sufficient, but it's also necessary for the limit to be Gaussian. Now I want to obtain, I know that under this assumption S is Gaussian, I would like to have a formula for the asymptotic variance and mean of this Gaussian for sigma square, what I'm representing by sigma square and mu. So I'll start with an observation. We have seen that for all f in CB star of R, the integral of f dm, we know that this is equal to 0 because we are assuming that the limiting distribution is Gaussian. Now what I claim is that, well, this entails also that for any x0, which is real number, the integral from minus x0 to x0 of x squared dm, it's equal to 0. So you fix positive x0, we would like to prove that this integral is equal to 0. And remember here, we are always assuming that the measure of the origin is equal to 0. Because we have uniqueness only under this assumption. So, well, instead of proving that, let me prove that this integral from 0 to x0, it's equal to 0. And here, maybe I'm taking that to be absolutely precise as the integral over this set. I'm removing 0, well, because anyway, x0 is equal to 0, and also the mass at 0 is equal to 0. And, well, the idea here is that I will rewrite the interval 0, x0 as the union of intervals, and let's call that x1, x2, so that 0, x0 would be equal to the union for n larger than 1 or larger than 0 of xn minus plus 1 xn. So let's consider a sequence xn which is converging to 0, and let's rewrite this interval as the union of these intervals in which I'm starting from 0. Now, I can rewrite this expression as the sum for, let's say, j larger than 0 of the indicator of the interval xj plus 1 xj x squared dm, and then I can use Tonelli to say that this is equal to the sum of the integral, and now I have an integral over a set which, well, this is function which vanish outside an interval. So this function, what I claim is that the integral of this function is 0, because I can always find a function f in CB star which it's larger, positive, and larger than this function, but since the integral of this function is equal to 0, this one it's positive, so its integral it's non-negative, but it's bounded below by 0 and above by 0, and therefore this integral is equal to 0, which means that indeed I can deduce from this identity the fact that for any x0 positive, the integral from minus x0 to x0 of x squared dm is equal to 0. So this is an observation which I'll use now in order to compute sigma square and mu. So remember that sigma square is the variance of the Gaussian random variable S. And we have seen, again, since mu n tilde 0 bn, it's converging to 0 sigma square mu. What we know from this limit is that if I take the integral from minus x0 to x0 sigma square d mu n tilde, since we have 0 here, that this is converging to sigma square plus the integral from minus x0 to x0 sigma square dm. But we have seen that this integral is equal to 0, so we have a formula for sigma square. Sigma square is equal to that limit. So let me compute this limit. So this is, by definition, the sum for j equal to 1 up to kn of the expectation. So we have here x squared. So here, remember, mu m tilde is the sum of mu tilde and j. So I will write immediately x n j minus a n j square. And again, we have here an indicator that x n j minus a n j it's bounded by x0. So here is a formula for sigma square. For all x0 positive, sigma square is given by this limit. I wrote it as equal. I'm sorry, it's a limit. So sigma square is equal to the limit as n tends to infinity of this quantity. And this is given by this convergence. So here is a formula for the asymptotic variance. I will now compute a formula for the asymptotic mean. So we have also, since this triple is converging to that one, this means that mu is equal to the limit of bn, and the limit of bn is the limit of an plus the integral from theta x. So remember that theta is that function which approximates x in the interval minus 1, 1, mu n dx. So this is the limit in n, and I will just write an. So an, it's the sum of a and j, and we can rewrite this as the sum in j of the expectation of theta x and j minus a and j. And in this way, we have a formula for the asymptotic mean. The formula of the asymptotic mean, it's equal to, we can write that in a unique sum, so it's equal to the sum of a and j plus the expectation of theta x and j minus a and j. And this is a formula for the mean mu. Now I want to conclude this lecture by proving Lindeberg's condition. So up to now, we assume that x and j, it's an array of independent random variables which are uniformly negligible, and that the sum is converging to a Gaussian random variable. Now I want to add two conditions. I will assume that these random variables, they have mean 0, and they have finite second moment. So I'm representing by sigma square nj the expectation of x n j square. And I will assume that sigma n square, which is the sum of the second moments, that this is converging to sigma square. So besides the previous assumptions, I'm adding the fact that these random variables have finite second moment, zero mean, and that the sum of the second moment is converging. And what I want to deduce, it's a second proof of the Lindeberg condition, which is that the limit as n goes to infinity of the sum from 1 up to kn of the expectation of sigma nj square, the indicator function that x and j, the absolute value, it's larger than delta, that the limit is equal to 0 for all delta. So this is what we want to prove now using the previous results. So, well, if you remember, this is exactly Lindeberg conditions, and so we are proving that the Lindeberg conditions are not only sufficient to prove convergence to a Gaussian, but that they are also necessary. So my first claim is that the sum of a n j square converge to 0. So let's remember the definition of a n j square. So nj is just the expectation of x and j with the multiplied by the indicator function that x and j it's bounded by 1. Now let's use the fact that the mean of x and j is equal to 0 to say that, well, this expectation it's actually equal to the same one in which I have x and j larger than 1 instead of x and j smaller or equal than 1. So this is equal to the sum of the expectation of x and j, and now that the indicator of x and j it's larger than 1. Now we can use this identity to say that this expression it's bounded by, so here I forgot the square. Remember, we have a and j square, so there is a square here. I'm sorry about that. And I will use Schwarz inequality in order to bound this expression by the expectation of x and j, the indicator that x and j it's larger than 1, times the expectation of this indicator function, but that gives me a probability that x and j it's larger than 1. And, well, I can move out of the sum this probability by replacing it by a maximum. So this is bounded by the maximum in J of the probability that x and j it's larger than 1. And here I have a sum of x and j, so I can forget about this indicator function and remember that what remains is the sum of sigma nj squared. So this is the sum of sigma nj squared, sum in j. So now I have a quantity here which is converging to sigma squared, which is finite, And on the other hand, since these random variables are uniformly negligible, I know that this maximum is converging to 0. So this sum is converging to a finite constant, this one is converging to 0, which means that this expression converges to 0, and therefore we have indeed that the sum of A and J squared is converging to 0. My second claim is that sigma square it's equal to the limit of the sum of the expectation of x and j square of the indicator that x and j it's less or equal than epsilon, and is for all epsilon. So I claim that for all epsilon positive, sigma square it's equal to this limit. And for that, I will use the formula we deduced for sigma square. So remember, sigma square was equal to the limit of the sum in J of the expectation of x and j minus a and j square, and the indicator that x and j minus a and j was bounded by x0 by for all x0. This is what we proved B. So let's see what we have here. So I will first decompose this sum. We have three terms. We have x and j squared. This one I will not touch. Then we have a and j squared. So this term converges to 0 by the previous. So if I expand this square, I get a and j squared times this, this indicator. This is bounded by a and j squared, and we have seen that the sum of a and j squared converges to 0. So this piece is not important. And then we have the cross term, and the cross term will give us, so let me erase this epsilon, this x0 to have some space. So we have the cross term, which is the sum in J, expectation of x and j, a and j. There is a 2 and a minus, but I don't care. I want to show that indicator x and j minus a and j less or equal than x0, and I will take the absolute value of this expression, and I want to show that it converges to 0. So I will use Young's inequality. Young's inequality tells me that x, y, it's bounded by 1 over 2a x squared plus a over 2 y squared, and this is true for all positive a. So I will use this inequality in order to estimate this quantity. So I'll say, and I will take a equal to epsilon. So I will bound that by, I have epsilon over 2, which I will use for x n squared. And so this is bounded by the sum of the expectation of x and j squared. And then mind that I will not use this indicator in this argument. And then I have 1 over 2 epsilon, the sum of a and j squared. Well, we have seen that the sum of a and j squared converges to 0. So as I take n to infinity, this term disappears, while here I get sigma squared. So we proved that the limit sup of this quantity is bounded by epsilon sigma squared over 2. Since this is true for all epsilon, this limit is equal to 0. So this means that in this square, the only term which does not vanish is x and j. So this limit is equal to the limit in which I replace the previous quantity by x n squared. Now I want to replace this quantity by the indicator that x and j is bounded by epsilon. And let me call that, maybe instead of x0, let me call that epsilon. So this was true for all x0. It's true for all epsilon now. Now, what I want to say is that this expectation, it's bounded by, well, we know that the maximum of A and J, it's bounded by, it's converged to 0. So since the maximum of A and J converge to 0, I can take n0 sufficiently large such that if n is larger than n0, then A and J is bounded by epsilon. So I fixed an epsilon, so the epsilon here, and I take n0 sufficiently large for A and J to be bounded by epsilon for all j. And now if I know that x and j minus A and j is bounded by epsilon, and A and j is bounded by epsilon, then I know that x and j is bounded by 2 epsilon. So this quantity here, it's less or equal than the sum of the expectation of x and j square, the indicator that x and j is bounded by 2 epsilon. So let me repeat, what I claim is that this expectation is bounded by this one. And why is that so? Because if x and j minus A and j is bounded by epsilon, and A and j is bounded by epsilon, then x and j, by the triangle inequality, it's bounded by 2 epsilon. So this quantity, it's bounded by that one. Sigma square, it's equal to the limit. This means that sigma square, it's less or equal than the limit sup of this quantity. Because, well, sigma square, it's equal to the limit of this sequence. This sequence, it's bounded by that one. Therefore, sigma square, it's bounded by this limit. You'll tell me this is not what I want to prove. I want to prove an identity. Well, but that's fine, because this expectation, it's bounded by the expectation of x and j square. Right, this expectation, it's bounded by this expectation. Therefore, this sum, it's bounded by this sum. And therefore, the limit sup of this sequence, it's bounded by the limit sup of this sequence. But this sequence, by assumption, it's converging to sigma square also. So I have a sequence which is bounded below by a sequence which converges to sigma square, and bounded above by a sequence which also converges to sigma square. And this means that this sequence converges to sigma square. So let me repeat. We proved that this expectation, it's less or equal than this expectation, which is less or equal than this expectation. This means that these sums, this sum, it's larger than this one and smaller than this one, but both sums converge to sigma square. The second one, this one, by assumption, and the first one because we obtained a formula for sigma square. So this was the formula we obtained for sigma square in as a consequence of all our arguments using triples, convergence of triples. Therefore, this means that indeed this sum is converging to sigma square, which is exactly what I claimed. So let me erase and keep only the conclusion of our computation. The conclusion of our computation is that sigma square is indeed equal to this quantity for all epsilon positive. Now, if you compare this expression with this one, you conclude that since I can write x squared as x squared times this indicator function plus the indicator function of the opposite, I will conclude exactly what appears here. Since this sum is converging to sigma square and this sum is converging to sigma square, it follows that this sum is converging to 0. And this proves Lindbergh's condition from our analysis of convergence of uniformly negligible sequence of independent arrays. And, well, okay. So this is the third point of this investigation of convergence to Gaussians. And I will finish this lecture by computing the asymptotic mean, by proving that the asymptotic mean under these assumptions is equal to 0. Now I want to prove that mu is equal to 0. We have a formula. We presented a formula for the asymptotic mean. The formula was that the limit mu is equal to the limit of the sum. So we have two pieces, A and J, plus the expectation of theta x and j minus A and j. So I want to show that these two sums converge to 0. So my first claim is that the sum of A and J converge to 0. So that will show that this quantity here converge to 0. This sum converge to 0. And why is that so? Well, this is the sum of the expectation of x and j, x and j less or equal than 1. Now, this is equal to the sum of x and j, x and j larger than 1, because we have seen that x and j has mean 0, so we can replace this indicator by that indicator. Now, since x and j is larger than 1, I can bound this expression. So you see, on this set, x and j is bounded by 1, so I can multiply everything by x and j to get that this is bounded by x and j square, the indicator that x and j is larger than 1. Right, because, well, 1 is bounded by x and j, so I just multiply this quantity in this set by x and j, which is larger than 1, to get an upper bound. And now I can use the Lindbergh condition that we just proved to say that this quantity is converging to 0 as n goes to infinity. So this proves that this first sum converges to 0, and now we have to examine the second one. Now let's consider the second sum, which is a sum of the expectation of theta x and j minus A and j. And what I claim is that the sum of the absolute value converge to 0. So what I'll do, I'll first fix an epsilon positive. So I'll show actually that this sum is bounded by this epsilon. And for that, I will first introduce in this expectation the indicator that x and j it's less or equal than epsilon. I have a second term which is x and j larger than epsilon, but this term is small. Theta it's a bounded function, so I can bound this expectation with the indicator of that x is larger than epsilon instead of x smaller than epsilon by a constant times the sum that the probability of x and j that this is larger than epsilon. And now I can estimate this expression by the sum of the expectation. For example, well, in this set, epsilon is bounded by x and j, so I can put here x and j square divided by epsilon square. I have the indicator that x and j, it's larger than epsilon. And this is by Lindenberg condition, this sum converges to 0 as n tends to infinity, and this holds for every epsilon. So I can indeed introduce this indicator, because if I bound theta by its L infinity norm, I have that this sum is bounded by this sum, and this one is converging to 0. So I can indeed introduce this indicator. So once I introduce that indicator, I want to remind you that theta x minus x, it's bounded by some constant x cubed, provided x is bounded by 1. So I want to introduce now to take out x and j, to add and subtract x and j minus a and j. So I have the piece with plus x and j, and this one I need to estimate. So I have to estimate the sum of the absolute value of the expectation of x and j minus a and j multiplied by the indicator that x and j, it's smaller than epsilon. Well, there is one piece which we already estimated. We have seen that the absolute value of a and j, the sum of the absolute values, converge to 0. So this takes care of this piece. And now we have to estimate this expression. But this expression, well, it's exactly what is a and j, where instead of epsilon, instead of 1, we have an epsilon. But we can just repeat exactly the same arguments to show that this expression converges to 0. This means that I can subtract x and j minus a and j to this expression, because by adding x and j, a and j, I get something which can be easily estimated, or more precisely, which has already been estimated. Now, once I introduced inside this expectation the term minus x and j minus n j, I can put the absolute value, bound this expression with the absolute value inside the expectation to get that this expression is bounded by the expectation of theta x minus and the absolute value theta x minus x and j, and this is on the set x and j, it's bounded by epsilon. So here inside the absolute value, I have theta x and j minus n j minus x and j minus a and j. Here I have the indicator that x and j is bounded by epsilon. For n sufficiently large, a and j, it's also bounded by epsilon uniformly in j. And see if I take epsilon smaller than 1/2, I have that x and j minus a and j is bounded by 1. Therefore, I can apply this inequality to bound this expression by a constant, the sum in j of x and j minus a and j to the cube, x and j less or equal than epsilon. Now, this cube I can estimate as follows. X and j is bounded by epsilon. A and j it's also bounded by epsilon, so this difference it's bounded by 2 epsilon. So this is bounded by C0 times 2 epsilon times the sum of x and j minus a and j square. And at this point, I will forget about the indicator function. So I have here epsilon, I have a sum. In this sum, I have x and j square, and this sum of x and j square will converge to sigma square. Then I have A and J square, but we have seen that the sum of A and J square, it's converging, the sum of A and J square is converging to 0. And I also show you how to estimate the expectation of A and J times X and J, and we proved that this is also converging to 0. So that this quantity, it's converging to C0 to epsilon sigma square. And therefore, we proved that the sum of the absolute value of this expectation is bounded by a constant times 2 epsilon times sigma square. Since this holds for all epsilon, this means that this sum is converging to 0, and therefore that mu is indeed equal to 0. And this completes this lecture. So we gave an alternative proof at the end of the Lindbergh condition using the theory we developed in these last lectures, and we also obtained, well, that the asymptotic formula for the asymptotic, well, we proved that the asymptotic mean is equal to 0 under these conditions. So this completes this lecture.